All right, so lastly here we have this noble gas notation. So it turns out that most of the time we only care about the outermost shell of electrons. So noble gases can be used to help shorten the process, right? They should have full shells, which is what makes them super unreactive anyway. So anything beyond that shell would be a new shell, and that's where you get your properties for this new element, whatever it is anyway. So we're going to use some we're going to use that noble gas to our advantage to shorten things considerably, excuse me. And then also D and F block are going to have some weird exceptions, but we'll talk mostly about F block exceptions because the exception becomes our rule, because it's more often that it's actually going to take place than anything else. So F block, we're going to have to do something special. Otherwise, if it's a D block exception, I don't really expect you to know it. So these are the examples we're going to try and do real quick. So aluminum, I'm going to do it the long way once, and then I'm going to show you how you can shorten it, and then do the other examples. So aluminum happens to be right here, right at the beginning of 3p, right? So I know it's 3p because I'm in the third energy level. And the noble gas that's immediately preceding aluminum is neon, right? So I'm going to utilize neon, but I'm not going to do it the first time. I'm going to do it the second time. So I got to go all the way to 3p. So normally I would go 1s2, 2s2, 2p, 6, and then I go 3s2, and then I go 3p, and aluminum's the first element in that p block, so it better be a 1, right? So again, I'm going to do this for anything bigger than neon typically. If it's smaller than neon, it doesn't really even save space to use noble gas notation, because all you'd be notating is this 1s2 as a helium, right? But that's already really small, so I don't care. But right now I want to recognize that if I go from 1s2 all the way up to 2p6, that would be my notation for neon, and that's where this shortcut comes from. In the future, I can just say, hey, aluminum's got all the same stuff as neon, but then it's going to add in the 3s2 and the 3p1. And that does shorten things considerably, so I don't have to worry about that 1s2, 2s2, 2p6, because in order to get to that third shell of electrons, the second shell had to be full, and the first shell previous to it had to be full. So I can use any noble gas to shorthand my notation. So when I'm doing bromine next, I just need to know, okay, what's the immediately preceding noble gas? So I can think about it two ways. 18 comes before 35, 36 is after, right? But I usually just go over and up one. So I know I'm going to start with argon, but then I have to realize, okay, argon's followed by potassium. Potassium's 4s, because that's where I'm going to enter my op-out principle. So when I do this, I need to start with argon, but then I enter 4s, and that should be full, because bromine's in P. But all I have to know is, okay, if I go way back, because it's inconvenient for me, 4s is followed by 3d is followed by 4p. So I just need to work from there. And then I can finish this off. 4s is followed by 3d, 10, and then bromine is in 4p, like we talked about, and it's 4p5 because bromine's towards the end. All halogens are p5s, right? So that would be my new notation, and it's a lot shorter than what I did previously because all of those inner shell electrons are represented by argon. Platinum, also not going to be a problem anymore. Used to be a problem because platinum has 78 electrons to deal with. So platinum's right here, it's in the D block. That should be 3D, 4D, 5D, right? Where I'm ending. And I'm going to start with xenon because that's the immediately preceding noble gas. Xenon is followed by cesium, which is in 6s. So I need to know that I'm going to go xenon first, and then I'll do a 6s2. And from there, if I don't know where to go, I go look at my off-bow principle, and I'm going to do 6s2, and then I'm going to do 4f, whatever, right? It's 14, 5d10, and then I'm going to get to 6p and finish this thing off, or wherever I was supposed to stop. I'm actually stopping at 5d, I think, actually. It's kind of like that one I had before, so I just have to do 6s, 4f, 5d, because I'm trying to get to platinum here, right? Just like when I was trying to do mercury before. I don't remember what I was doing. Sorry, I keep pushing the wrong things. It was mercury before. But 6s is followed by 4f, 14. 14 is a full F sublevel. And then I go 5d. And again, platinum, you need to know where it is 2 away from the end. So that's 2 less than 10. That's how I think about it. It's going to be a 5d8. I can check my math. Again, I could still add up all these electrons. I just 8 plus 2 is 10, plus 14 is 24, and then 24 onto 54, because that's what xenon has, would be my 78, which is correct. That's what I was supposed to have. So I could check my math every time. I rarely do, because I just assume I'm not going to make a mistake. Now, that being said, we make lots of mistakes, so it's okay if you do, but on to the next example. Calcium would be here. So it's only got 20 electrons, but I'm still going to cut things quite a bit. So argon is my noble gas. 4s is where I'm at. So this one's really short. I just do argon and then 4s2 because calcium has 2 electrons in that s sublevel. It's the second element. So finally we have this lanthanum and actinium, right? These are both F block elements, and they're both the very first element in the F block in either row that you're looking at. So they're special case things, and we're going to use these to model off of. That's why I'm doing these 2 examples. But lanthanum and actinium, right, a little bit harder to see what noble gas is preceding because you have to kind of backtrack, right? Because lanthanum really fits right here. And then you go barium, cesium, and then you get to xenon over here. But again, if you look at the number, 57, 54 precedes it, 86 is after, right? So I know I have xenon to start. Xenon is at the end of, it's 2p, 3p, 4p, 5p, right? So 5p is followed by 6s, and then I do what I got to do. So lanthanum is xenon followed by 6s2, and then usually you would go to 4f like platinum up here, but since lanthanum's an exception, something different happens, right? For anything that's F block, you're always going to put 1 electron in D before you start putting electrons in F. And that's just a weird thing that happens all the time, right? And it's an exception that we're memorizing because why not? You always want to memorize the exception if that exception is more common than the normal rule, right? So for most of the elements that we'd be concerned with, this is going to happen. And the only reason it wouldn't is explainable later. So xenon 6s2 5d1 is correct for this. You skip over that 4f that I used for platinum up here for a reason. So it's going to seem weird, but you're just going to do that always if you're in the F block, right? Actinium is similar, right? Except actinium is radon followed by 7s followed by a D instead of going to F. So radon is how I start actinium. And then I go 7s2. It should be a 5f followed by 6d, but I'm going to put 1 electron in 6d right now. So it's 6d1. And again, the reason I'm doing this is because I can model off of either one of these because these are correct for anything that's in that F block, right? So when I look at an element in the F block, when I see uranium here, number 92, I don't worry about anything else. I just know it's actinium plus 3 electrons. That's all I have to care about, right? Because actinium's here, 1, 2, 3 more electrons, and I got uranium here. So that's what I'm going to do. I'm going to literally write down exactly what it says for actinium, and then I'm going to add 3 electrons into that 5F that I had skipped over previously. So 5F is just going to have a certain number of electrons, right? So if I'm going to model off of actinium to do anything that's F block, right, I just need to fill however many electrons are left in F. So whatever number is left here, I could, I don't know, just put X for some value that I don't know. But if it happens to be uranium, right, again, I just do the whole thing. I can't say actinium, but I can do radon, and I can do my 7s2, and I can do my 6d1. This is what actinium would normally be, but then I'll just do 5f3, because again, I don't count actinium, because I already dealt with that 1 electron that's in that D sublevel, but then I go 1, 2, 3 more electrons, and I get to uranium. So when it's all said and done, that's how I deal with F block things. So this is a good example for uranium. Otherwise, if I was in that lanthanum row, I would do the same thing. I would start with whatever I have for lanthanum here, and then I would do 4F, however many electrons I need. So that's why I want those 2 examples in your notes, because those would be correct for lanthanum and actinium, but that purple or blue that I put in there, that should also be a different color in your notes if you're going to write it this way, because that's not going to be anything you'd need for lanthanum itself, but it'd be what you would need for any element beyond lanthanum, like the cerium. I can't read that. I can't pronounce half of these things anyway, but any of these elements that are in this row that I'm clicking on right now, those all would start out the same way. They'd all start out with xenon, 6s2, 5d1, and then 4f, however many electrons I need. But again, if I was doing this promethium here, number 61, lanthanum has already been accounted for with a D1. So I'm just 1, 2, 3, 4 electrons in. It'd be a 4F4 for that one, right? So again, I know that's kind of confusing, but hopefully you have enough examples that you can work off of, and we can practice it in class.